All right, it's starting recording. Okay. All right.
Yes, ready to go.
All right. Well, how's your day been? And can you tell us who you are for those who don't know?
Yeah, I'm David Ospness. I spent 25 years with Bell Labs, and then I retired in January after 32 years at NC State in the Department of Physics. So I am a physicist. I have worked on optical properties of materials and generally electromagnetic interactions with matter. And I am now doing work on data analysis. So that is an overview of what I have done and a bit of my background.
Okay. Today, I decided to pick one unresolved mystery or problem in physics concerning antimatter. Can you tell me what it is, a brief explanation of what it is and why it's a mystery?
Yeah, antimatter is evidenced by the fact that it recombines with matter and generates radiation. For instance, an anti-electron will combine with an electron and produce two gamma rays. The energy of the gamma rays is equal to the energies of the antimatter positron, as we call it, and the electron by Einstein's equation, E equals mc squared. And the question about what is antimatter, really, we need to define what is matter. And since we don't really know what matter is, all we can say is that antimatter is the opposite of matter. The nearest thing that we can probably describe matter as being is it's a state of energy that's stable. And again, we know it's energy because when we convert the particle to radiation, we get E equals mc squared for the energy of that. So the fact is that we don't even really know what matter is, let alone antimatter. All we know is that when the two get together, then they generate a pair of photons, gamma rays typically, because the energies are fairly high.
Okay. Okay. And can you explain why this would make antimatter? Well, the two major problems I've read are that we can't produce it and we can't store it. Can you explain why those are problems? As opposed to say why we can deal with oil or other forms of energy versus antimatter?
Yeah, the problem of creating antimatter is that we can create small particles like like positrons, and we can even create antiprotons. That's been done, for instance. But when you're talking about creating an anti-building, for instance, which would be composed entirely of antimatter, we can't do that. First of all, it takes too much energy, and secondly, it's unstable. Any particle in that building that met up with a particle in the real world would immediately annihilate, generating gamma rays. And so we cannot keep an antimatter structure distinct, separate enough from matter in order to have it be stable over long periods of time. We can do it for short periods. Antihydrogen has been made, for instance, and kept in storage, but the storage is ultra high vacuum because as soon as it contacts any aspect of matter, it is annihilated. So it's a question of being able to isolate the antimatter for long periods of time, and not only talking about the energy required to create the stuff.
Yes. So if it is annihilated, as you say, if it comes into contact with any matter, isn't the air we're breathing made of matter? So that means it could even come into contact with air directly.
Oh, absolutely. Air is a combination of it's a mixture of nitrogen, oxygen molecules, water vapor, some lesser materials, but air is entirely matter. And so contacting air would be fatal to any antimatter particle.
Okay. Okay. And I guess going back to the production problem, if we always make matter and antimatter in equal quantities, as in if we create an anti-electron, we create an electron, Why are physicists studying it? Isn't that the end of the story, or are they trying to say that you can create it in different quantities?
No, it's really a question of fundamental physics. Why does matter exist? Why does antimatter exist? Elaborating a bit on my earlier comment about making the stuff, what we typically do is we create isotopes that are unstable. Fluorine 19, for instance, wants to decay into oxygen, and in the process, it emits a positron. And so we create, if you will, use that term, we create a positron by making fluorine 19 and watching it decay, which is not really a process that's totally under our control. It's still decay is a random process. But now I got to the point where I forgot your original question. What was that?
It's can we make them in unequal quantities, or if we could,
Oh,
what
okay.
would that?
Yeah. Again, it's a question of energy input, and we just don't have the capabilities of, well, what is it? The electron energy is 511 kilovolts, half a mega electron volt,
Yeah,
and that's a lot of energy. I think at one point you had calculated the amount of energy required to make a gram of antimatter, and a gram is really nothing. You can't do much with a gram. And it was something like the capacity of the US power system for appreciable amounts of time. So
yeah,
we just aren't set up to do that, nor would we want to, because this stuff would be highly dangerous if we could make it in bulk.
yes. I think the sun produces antimatter and like solar flares, but it at most it produces like a kilogram, but even that would be exceedingly dangerous.
Yeah, this sun is a nuclear reactor, but it's well shielded. so,
Yeah.
so we don't worry about that. And we don't
Okay.
worry about the antimatter it might create. We're still
Right.
well shielded.
Right. So I guess when you're saying it, when you think about other power sources like say hydrogen or gasoline or even nuclear fuel, I guess that's because the fuel is already there. We just have to mine it. We have to extract it. But with antimatter, as far as scientists know, all of it was destroyed long ago. There's nothing to collect, in other words.
That's right. You are not going to find a mine of anti carbon, for instance. Coal, anti-coal doesn't exist. So no,
Okay.
you can't. You're not going to find something like that and then exploit it to generate power. It's not going to happen.
Okay. Yes, I did a calculation that said 1 gram is equal to something like 90 terajoules. Uh, if which is the same as 90,000 gigajoules. If all nuclear power plants in the world produce about 400 gigajoules, that's too much. One, we can't produce that much in one spot, and two, it would destroy any power grid.
Yeah. Okay. So we're consistent in that antimatter is a laboratory curiosity, but does not have any practical. And well, actually, I'm going to change that too. And curiously enough, Physics Today, which is the monthly publication of the American Physical Society, came out in the issue this time with an article on the use of positrons to do diagnostics. And what they do is they make compounds that adhere to prostate cancer, for instance, and the compounds contain elements that I'd mentioned, like fluorine 19. And as they decay, then you look for the gamma rays coming out. And so you can see where the source has attached, and then you can tell where the cancer is, for instance. So these things are used in diagnostics, but they're not used in bulk, as which is what you're driving at.
Okay, yes. And since you studied a lot of engineering, even if you let's say you could bypass the production and storage problems, right? And let's say I had it, how would you even make it a practical power source? It would destroy everything, right? I don't even you can't make it into a battery or anything, right?
That's
We
right.
don't even have
Well,
nuclear batteries.
it'd be highly dangerous because to store the stuff already is a problem. If you had any leakage, you'd have enormous explosions. Okay. because my guess is that the first decay product would destroy whatever uh, environment you were encapsulating the antimatter in. And of course, then it would just run wild. You'd have a chain reaction.
Okay.
Very,
Okay.
very dangerous stuff.
Okay. So, what do you think the solution is, or do you think physicists will find a solution to the what they call the missing antimatter problem or baryon asymmetry? Or do you think there's just antimatter somewhere else that we can't see?
Well,
Because then
that's
you would
that's
be able
different
to.
from that's different from the engineering problem of what do you do with it.
Right.
This is a fundamental question that physicists have been struggling with ever since the discovery of antimatter. Is that why is the universe consisting entirely of matter? Well, we know the antimatter annihilates, but that's really not the point, because if you can't create an antimatter particle without this, well, actually that's not true. It's charge that's conserved, not the particle. I can create the positron, and I don't have to create the negative electron. But what I do have to do is I have to change the charge of a proton, or basically a neutron, goes from being neutral to being well, negative. How does that work? There's no negative. I'm out of my depth on this one. But if the well, okay, if fluorine goes to oxygen, then what's happened is a proton has turned into a neutron and emitted a positron. So you still have total charge at the end is the same as the total charge you started with. And that tells you that there's a problem here anyway, because neutrons will decay. Yeah, okay. So neutrons are unstable, and I guess they just simply decay into positrons and protons when you get down to it. And so then the positron finds an electron and annihilates, generating two gamma rays. So that's the story then of where these things come from. Neutrons are intrinsically unstable in free space, and they decay into a proton and a positron. Yeah, okay. I learned a bit now in the interview here. But as far as the universe consisting only entirely of matter, that's a puzzle. We should have just as much matter as antimatter, really, and we don't.
Yes. And also, I was thinking that uh, I think to conserve charge in a neutron, it's made of three quarks, two down and one up. And then and then a proton is made of two ups and a down. So if
Yeah.
you turn a neutron into an anti-neutron, you're flipping the sign of the charge on the quarks.
Well, you're turning a neutron into a positron and a proton.
Okay.
No, let me stop and think a minute. No, we're getting there yet.
Yeah.
When a neutron decays, it generates a proton and an electron. Okay,
Right.
not a positron.
Okay.
And so that your charge is still the net charge of the system is still zero. Okay,
Okay.
and what's resulting are two uh, matter particles, not antimatter particles. And so neutron is a matter particle, and it decays into two matter particles. Again, no antiparticles.
Okay. So if I had a device and I could just put in, say, protons, right, which are positively charged, and I
Yeah,
could just produce antiprotons, which are negatively charged, that's destroying electric charge conservation, isn't it?
that's correct, and that would not happen.
Okay. Okay, that's why we can't make them in unequal quantities. Okay.
Correct. That's really it's the charge conservation problem that you're running into here.
Okay. Okay, and that can't happen. Okay. All right. Uh that's pretty much all the questions I had. Do you think does NC State study antimatter at all? Or you don't know?
We don't have any programs that are dealing specifically with antimatter. There are theorists that are worried about the problem, and we have a strong program involving neutron spectroscopy. And so, but that again isn't an antimatter thing. I think the problem that your generation is going to have to deal with is why do we have matter in this universe and no antimatter? It's not a question of annihilation. It's a question that when the universe started, we had more matter than antimatter. And so by the time all the antimatter got destroyed, there's still matter left over. And why this asymmetry? That's a puzzle that hasn't been solved yet.
Yes. And I don't know how to solve it yet, but hopefully someone will figure it out one day.
Well, we'll get there yet eventually, but we haven't
All right.
got there yet. A
All right.
challenge for your generation.
All right. Well, thank you for your time. That's basically the whole interview.
Okay,
I'll
a
stop the
pleasure.
recording here. All right. Thank you. I'll stop the recording here. Then we can talk and I'll
Yeah.
let you go. Hold on. Stop recording. Yes.